Okay, so we are now starting the bottom of page 216 and the dynamic equilibrium of a system. So equilibrium, okay, so this word entails an idea of balance. So if your life has balance or equilibrium, that means that you have gotten really good with managing all of your life processes and things going on in your life. Maybe it's your academics, playing a sport, getting your studies done, family chores at home, all the things that need to be continuously accomplished. And we refer to it as a dynamic equilibrium because when people on the outside look at your life and they see that it's in equilibrium because you have good management skills, they see everything running so smoothly that they don't realize that things continuously need to be done. So if it's dynamic, it means that all of those life processes continue on. So that means that that whatever the process of change and what needs to be done, the process does not stop. And so I like to use the symbol of like a teeter-totter from the playground to represent the idea of equilibrium, finding that balance. And in the world of science, we have three major types of equilibriums we look at: phase equilibrium, solution equilibrium, and chemical equilibrium. So in class, okay, we worked on an activity where you started off with, we defined the reactants of this beaker containing 60 milliliters of water, and the product container was empty. So there were no products present. And then we used these straws to transfer water back and forth between the two beakers. So at the end of trial 1, we saw that the reactants total volume changed. It was no longer 60, but it ended up at 40. And we saw that the reactants went from not being present to now having some products present. So if I was to draw a graph to represent this idea, okay, so here we go, idea of equilibrium. So the x-axis is time and the y-axis will represent a molarity of concentration, and we're just going to say that the volumes we measured are those concentrations. So initially we have reactants but no products. So our reactants start up here, and I'm going to put an R, and no products, so starts down there. But we notice initially the reactants concentration during trial 1 decreased. The products went from 0 to 20, so the products went up. And then we went and we committed a couple more trials. So let me fold down. So we noticed that trial 2, the reactants concentration continued to decrease, but then in our trials 3 and 4, the reactants concentration or volumes became constant. So overall, I would show a decrease, 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 and then where it starts to remain the same. And we saw a similar trend with the products, where the products had nothing, increased to 20, continued to increase to 32, and then on our last couple of trials, it remains the same at 39. So we see this flattened out. So at this point where we see that our line flattens out, okay, we are at a place of equilibrium. So from this place over where it's all flattened out, we are at equilibrium. And since we're reading concentration off of the y-axis, if we are at equilibrium, we always have constant concentrations. And sometimes the pet name for those constant concentrations could be referred to as con-con. So constant concentrations, we have reached con-con. Now, here is the other major idea. Okay, so drawing a similar type of chart or graph. Okay, so we have our time, but instead of having concentration, we're going to have the rate. So since we start off with reactants, the reactants are going to react to make the products. So here we go. But since there are no products, the products cannot, since they don't exist at this point, they can't form the reactants. So here we're looking at, so the rate of the forward compared to the rate of the reverse. So remember, forward is our traditional reactants making products, but if we're talking about the reverse, we're talking about the products reforming what we refer to as the reactants. So when we look at from the initial to trial 1, we see that the reactant amount decreases because the forward reaction is favored and it's happening. Okay, and then as we look at the second trial, now that we have some products actually present, okay, we can see that they are able to make some reactants. So initially the forward reaction is really favored and happening, but it starts to slow down as the amount of reactants present starts to decrease, less collisions there. We see that the reverse reaction starts to happen, okay, because the products are there to reform the reactants. But then when we look at our last couple of trials, we see that things start to even out because the concentrations are not changing, so the reactant rates must come to a place of equilibrium and matching each other. Matching each other. So once again, we have this flattened area. So when we get to this point, right, this point forward, we are at equilibrium. So notice that the forward rate is the same as the reverse rate at equilibrium. So we have equal rates. And when we have equal rates, sometimes you will hear me say the idea of requal. So equal rates, our pet word for that is requal. Okay, so now back to the notes. So dynamic equilibrium, I hope you jotted down those graphs. So number 1, we have con-con, and number 2, we have requal. So, and what that means is that during phase equilibrium, okay, our rate of melting solid to liquid will equal our rate of freezing solid or liquid back to solid. Or we could have our rate of boiling, which is another major phase change, is the same as our rate of condensing. So our rate of liquid forming solid is the same as solid forming liquid, or a gas condensing to liquid equals the rate of the liquid forming the gas. For solution, okay, this means that our rate of dissolving equals our rate of precipitation. And if our solution is at equilibrium, then we always say it's a saturated solution. And then, once again, a chemical equilibrium, the rate of the reactants forming the products must equal the rate of the products forming the reactants.